Thanks again, Boris, for joining. And the floor is yours.
Thank you very much. Hi, everyone. It's very nice to be here. Very happy 2025 to all. And yeah, today I'm going to be talking about some of our latest work in the NVIDIA Autonomous Vehicle Research Group on revolutionizing AV development with foundation models. And in particular, I want to start with a quick overview of where the AV industry is today in terms of advanced driving assistance and where we want to go and what we need for the future. So right now we already have quite good advanced driver assistance systems that are already in the hands of consumers. And we even have fully driverless operations in certain operational design domains, certain cities, certain areas, certain times. And all of this advancement has been powered by the judicious incorporation of certain types of machine learning and AI into the AV stack. And what we're really interested in for tomorrow is tackling the problem of generalization. How do we handle new deployment domains? How do we handle weird things that we see in the world that we might not have ever seen in the training data set that are completely unseen? And it's really a big question of how we can generalize to this long tail of unseen scenarios. And the hypothesis that we've been investigating in the group is that foundation models might be this key enabling capability to provide AVs with long tail generalization capabilities. And in the talk today, I'm going to show examples of how we can really boost AV development by using foundation models in both offline processes like auto labeling or simulation, and also even empowering the onboard vehicle stack. And I'll show some examples of that too. Now, of course, safety is paramount in all of this story. And actually, we found that foundation models can even help bolster the safety of such systems. However, in the keeping in mind time, I'm not going to go too deep into the safety frameworks, but I'm going to present a few slides that provide an overview of the kind of frameworks that we have in mind and that we're developing within the group here at NVIDIA. So before diving into all this, I want to give a really quick overview into what I'm referring to when I say foundation models and what it looks like to build them, at least for specific for AVs and robotics in general. So generally, the architecture of foundation models looks something like this. We have multiple different types of data sources and data modalities that are encoded into some kind of a shared latent space. This latent space is often referred to as, either embeddings, vectors, or even tokens. And these tokens are then processed through some kind of a sequential transformer backbone. Here I'm showing an example, very commonly used like a large language model as a backbone. And then the output of this model is some output tokens or embeddings, which can then be decoded into task-specific outputs that are of interest to the downstream task at hand. Now, there's a lot of choices. I mean, even if the architecture might look like this, there's a lot of choices as to how you could train, what data do you use to train this model? What are actually some of the specific model choices that you make? And then what are the tasks that you either train or fine-tune this model on? And I'm going to show two examples of, let's say, the most dominant examples of foundation models that we've seen within the AV and robotics space to illustrate some of the choices that people have made in building such models. So the first really common paradigm that we see within the robotics and AV community is multimodal large language models. These are models like Gemini, GPT-4, or in the academic space, Lava or Palmy. And these models really focus on breadth in terms of they all train on internet scale data, but they train on really a variety of data. So you might see the representation of text in there, of images, of videos, and with many different downstream tasks that they're training on, like text completion or image or video generation or captioning, or fine-tuning tasks like visual question answering or different reasoning tasks or things like this. So it's really a breadth of capabilities on a really massive data scale. And typically we see that autoregressive transformers are used as the backbone architecture. And just to show a quick example of what this can look like in the AV space, I'm showing here, um, imagine that you are a tourist visiting Mexico and renting a car and driving around. And, as you're kind of on a rural mountain road, you start to see these kinds of road markings, these arrows on the road. What do they mean? I don't know. There's no signs or anything telling you about, what's actually going on here. And so what we did was we actually asked a VLM, a visual language model, to help us parse through what's going on here and understand what we should do. And this is a work I'm showing an example of an output from a work in our group that was at CVPR 2024. And we can see that the output of the model is actually telling us that we should follow these arrows and switch to the opposing lane, because they indicate, actually what these arrows are indicating is that because there's a blind turn coming up ahead, the local officials have said, you know what, let's give people more visibility, more sight lines, and allow them to use, the opposing lane in order to drive and see around the corner. And so even if we might not have, any idea of what's going on here, because VLMs are trained on such a broad swath of the internet, they actually have some kind of prior knowledge that we can leverage here. So this is but one example. Another really common architectural paradigm that we see within the AV and robotics space are video generation models. So these are models like Sora, Gaia 1 in AV, or even general models like DALI and Stable Diffusion. And these works, they focus very specifically on the visual domain, modeling images, modeling videos in particular. And, we've seen a variety of infrastructures, architectures tried for this, from transformers to diffusion models purely. And now I think I see some hybrids like diffusion transformers. And what we see a lot of in robotics and AV is the idea of using these kinds of models to actually generate new data. And here I'm showing some examples from actually some earlier models, some earlier Cosmos models, which are very recently released models by NVIDIA that were trained on, these were specifically fine-tuned on AV data. And what's important is that we can, generate kind of not just single camera videos of scenarios, but actually multi-camera geometrically consistent videos, which are very important in the AV space. Here I'm showing 3 camera examples, but this model can also generate 6 camera examples. And so this is really kind of mimicking what you would see really like a surround sound view of the car. And well, at least months ago when we were working on this kind of preliminary model, it was very exciting to see these kinds of results. There are still, of course, failure cases, right? And you see a lot of these kinds of hallucinations where you see objects kind of transiently coming in and out. And so what we're envisioning really is that while we do have these two paradigms of, multimodal large language models, video generation models, and right now they're kind of being built independently, what we're really envisioning is a world in which they actually unify, perhaps by aligning their latent spaces and using the same shared latent space to leverage, the visual prowess of video generation models with the broad, multimodality of multimodal large language models to really try and get the best of both worlds. But at least as of yet, that's still a hypothesis. That's something that we're working towards. Now, given that we can, kind of have these kinds of tools at our hands, how can we use AV foundation models? And as I mentioned, I'm going to talk about offline processes and the online on-vehicle AV stack. So one of the most important tasks in the offline space of AV development is simulation and really understanding how your stack is going to do well in either scenarios it has seen or maybe with some slight changes. And an important part of building any simulation is actually building a good environment and a good reconstruction of maybe environments that you've seen either via log data from, for example, drives where you've been recording data. Now, one of the most difficult challenges there is to actually understand and parse out the different aspects of your environment so that you can actually reconstruct them accordingly. And I'm showing here an example of a work from our group at last year's iClear, where we came up with a nerve-based solution that was able to, in a self-supervised manner, decompose static and dynamic parts of the scene. So here you can see, our model is able to segment out dynamic objects, their flow over time, like their optical movement, as well as the static objects here. And this is very powerful because, being a NERF-like approach, that means that you can actually, out of the box, immediately have novel view synthesis capabilities, which is what I'm showing on the left. And you also don't have to just reconstruct RGB observations, but you can also reconstruct other kinds of sensors like LiDAR, because you have a geometric understanding of the world, because NERFs themselves, especially with dynamic NERFs like this, you're able to model 3D and actually the 4D spatiotemporal world. Now, why I'm bringing up this example is because with this kind of an approach, yes, you can reconstruct sensor data, but you don't have to. You can also reconstruct sensor data and foundation model features. For example, features from Dino V2, which is a model from Meta, or Clip, which is a model from OpenAI from a few years ago. And this is very powerful because it allows you to make different kinds of queries in the NERF's geometric space using this latent information that you've been able to distill into the model. And I'm going to show some examples of what that looks like. So on the bottom left here, I'll show an example of where we distilled clip features, which are features, it's a model that's been trained to align language with images. And what you can see is when we query in text for cars, you're able to immediately get this very powerful auto labeling capability out of the box in the NERF. And you can see that all cars, all pixels related to cars are actually lighting up as matching this query. Another example here on the bottom right shows the distillation of Dino V2 features into the NERF space, which, when you re-render these, here I'm showing it in 3D, actually a 4D view, you can see that similar semantic concepts are clustered together. You can see all cars are kind of this light blue. You can see traffic infrastructure is in green, buildings are purple, maybe trees are brown. So you see, you can get this really powerful auto labeling capability just out of the box by using already pre-trained foundation models that other people have made and released to the public. Now, even though I'm really happy with these capabilities, there are still three core caveats with this kind of an approach. The first is that NERF fundamentally is a per scene optimization based approach. What that means is that for every single scene that you get, you have to redo your optimization of the scene. And unfortunately, that optimization process can be slow. So the first is that it's, we have to do per scene optimization. The second is that unfortunately that per scene optimization is slow. And the third is that these reconstructions are reconstructions. All the agents are only going to do what they did in the scene, all the other traffic in the scenario. And so, in simulation, we would like to change things. And so we don't really have a way of doing that just using this approach. So I'm going to talk about how we tackle these caveats and show how foundation models even come into the mix for all of those. So first, we tackled this problem of how we actually remove the need for per scene optimization. And really the main way that we did this was by changing the internal representation that we used. Before, with NERFs, you're using a neural network to essentially model your scene and query it repeatedly to give you, details of rays, of light rays, and what colors are along those light rays. Here, rather than going from NERF, which is purely implicit, we're actually going towards an explicit representation. And by example here, we used sparse hierarchical voxels to model the world, which is great because this representation can now give you a direct differentiable path from input observations. And that means that you can now generate this kind of scene world representation in a feed-forward inference manner. And what that means is that you can also train on multiple different scenes at the same time. And we can use all the same rendering machinery that we did with the NERFs before in order to actually, the same exact training tasks. But now with the benefit that we can do the exact same kind of distillation that we did before. We can use foundation models. We can even use some of the pre-trained NERVs that we used before. And what this allows you to do is it allows you to, I know there's a lot going on in this image, but it allows you to retain all of the exact same outputs that you had before. Depth, clip features, Dino V2 features, all those abilities to query things and see the, auto labeling. All of that you can retain, but now you can train beyond just one scene. You don't have to just rely on per scene optimization, which can be very slow. And and just quickly to say, all of this is actually a work that we presented very recently at NeurIPS 2024. And, talking about speed, when you have a neural reconstruction approach, you have two core choices that influence speed, and they influence different kinds of speed. So the first is the actual rendering speed, so how fast you're actually able to come up with your images of multiple sensors. And then the second is the speed of actually obtaining the neural reconstruction. And as I talked just in the previous slide, we can have representations like voxels, which give they kind of determine how you can render things. But there are other choices which give you much faster rendering speeds. And a very common, very popular choice nowadays is 3D Gaussian splatting, which is really lightning fast to render because it is an excellent explicit representation that only basically models occupied surfaces and objects. And it's an explicit representation, so there's very, very fast methods of rendering it. Now, as I said before, you know, there when you have to do optimization to obtain this, it can be very slow. And so something that we've been looking in the group, as I mentioned before, was feed-forward inference. And to give you an example of what that looks like, you can imagine having a model that for every pixel in an image tries to estimate where there might be a Gaussian placed along the ray that's determined by that pixel. And then you can try and kind of learn this depth map for every, across multiple images or scenarios that you train on. And what this does is it changes your reconstruction approach from an optimization-based approach to a purely feed-forward inference-based approach. And this is something that we saw on the previous slide, but this is just kind of diving into what those mechanics look like. And when you now put both of these pieces together and you go towards this much faster to render 3D Gaussian splatting representation, you obtain Storm, which is a new work from our group that's just recently been released on arXiv. And this method basically puts together the best of both of those worlds and allows you to reconstruct large-scale urban driving environments in less than a second, where otherwise they may have taken multiple minutes if you tried to do optimization. And we still retain this very fast rendering capability that Gaussian splatting gives you, which is able to actually render multiple camera images at 100 plus FPS. Of course, with different numbers depending on if you have, how many cameras you're rendering at the same time. And there's a lot of really powerful things you can do with this because that explicit Gaussian representation, in contrast to the voxel one that I showed you, allows for a lot of powerful things like explicit scene editing or control of actors, because now you have very explicit objects in 3D space that you can manipulate yourself and you can move through space. Now, the third caveat that I mentioned was that these reconstructions are fundamentally reconstructions. That means that agents are only doing what they did when you observe them. And what I'm showing here is, our group has done a lot of work over the years on traffic simulation models and agent behavior models that you can use for simulation. And I'm just showing here just an example of some of the works that our group has done. But one thing that's important to keep in mind is that unfortunately, when you have traffic simulation models and you have to now specify a map or you have to specify the initial condition of agents, there's still a lot of labor that's involved in setting up these kinds of simulations. And something that we looked at also in the group was how to simplify this interface to simulation and how to allow users more flexibility and a simpler time actually setting up these kinds of environments. And what we looked at was transforming, actually using text as a natural interface to simulation. And you can imagine immediately the kinds of capabilities that you can enable with text, like, for example, scene editing, as I'm showing here, or something that we were really striving to do with this work was to actually enable full scene generation just from text. And why that's important is, yes, it enables users to set up simulations a little bit more easily than kind of what you had to do manually before, but it also allows you to use other sources of text descriptions for traffic scenarios. A really key example being crash reports. Crashes are things that are really hard to observe if you're just collecting data yourself. You probably have to, collect billions of miles of data before you actually see an appreciable number of crashes. Whereas what we can do with this kind of a framework is leverage text from police reports, from insurance reports, or from state and federal databases to actually obtain long form descriptions of real world accidents that happened and now reconstruct the motions of vehicles that were involved in that accident, and then also feed that information into photorealistic simulators. Here I'm visualizing Drive Sim, which is an NVIDIA photorealistic simulator for driving use. And here I'm showing kind of three different scenarios which we were able to reconstruct and then render in this environment, which I think is a really powerful capability. Now, this was a work that we presented at Coral in 2023. We've since advanced this method because, text alone, while it's helpful at setting things up like this, it's not a very exacting specification. If you want to say, I want a car at exactly, 4.5 meters ahead of me right now, a lot of models struggle to take that very exacting specification into mind and actually apply it. And so what we've been looking at within the group this year was enabling users to provide more kinds of prompts for these kinds of models to specify traffic behavior. And in particular, we looked at more than just text, but also goal point specifications or course sketches of trajectories, and also even discrete actions, like if an agent is stopping, turning, parked, etc. And you can see some examples here of how just from specifying different kinds of prompts, even in the exact same scenario, you can get very different kinds of agent motions. So I'm showing here some examples from the Waymo data set. And this paper is now, and the code and everything is up online. This was at this year's Coral, or at 2024 Coral. And what's important about the way that this model works is, yes, it can bring together all these different kinds of prompts, into one architecture, and it can leverage that information. But actually, I think one of the most important facets of this model is that actually the output, whereas traditionally it would just be trajectories, just explicit trajectories that then you execute in open loop. Actually, this model outputs policies, and these policies can then be executed in closed loop in your simulation environment, which is really powerful, because then it means that these agents are actually at every step reacting to the kinds of local observations that they have and reacting to how your ego vehicle may be performing. So this, I think, is also a powerful capability of simulation traffic models going forward, is really keeping that idea of closed loop simulation, closed loop evaluation going forward. Now, where we're going with all of these works combining sensor and traffic simulation is the capability to really take something that we've seen before in the world, which might be benign, might be boring, and change it a little bit to now, still keep that element of realism, but really bring us closer to what safety critical scenarios might look like. So I'm going to show an example here of, I'm taking just a log from the Waymo data set. So this is just normal driving behavior that was captured in the Waymo data set in San Francisco. And you can see it's a simple scenario. We have a car approaching a four-way intersection, and then another car stopping and crossing through. And in the bottom video, we've changed a little bit of the motions of one of the agents here to make now this kind of benign scenario into really something that could be potentially quite dangerous. So I don't know how well the video is kind of coming across the recording here, but what you can see is that vehicle that did otherwise stop on the left before going through the stop sign now actually drives straight through the intersection at a very high rate of speed. And we're able to do this by combining this ability to modify the motions of agents, but also rendering them in an accurate photorealistic manner. And so I think this is really, this is exactly the kind of powerful capability that we want to enable with all of these advancements, the ability to modify scenarios, but still maintain, the realism of how they might be actually observed by an autonomous vehicle. So with that, I'm going to talk about how we can bring this kind of technology also onto the on-vehicle, onboard side of things and actually advantage current stacks with them too. So earlier last year at CVPR, our group was seeing this kind of tide turning towards end-to-end AV stacks, AV stack development. And there was still a lot of uncertainty at that time of what is actually the best AV architecture, what is the best set of modules to use, what is the best set of representations to use, and which modules are actually needed to achieve good driving performance. And so there was still quite a lot of choices that were left up to practitioners in the AV space around that time. And what our group did was in this specific work, Paradrive, what we did was we developed a computational graph framework that allowed us to experiment with these different choices, different representations, different modules, different module orderings. And when we did our kind of a widespread experimentation to find the best kind of an architecture, the best performing architecture, what we actually found was that this archetype, I should say, on the bottom left, was actually the best performing. And what's going on here is instead of having a cascaded chain of modules, what we now have is, we have our sensor input, which is then, being encoded and then, used in parallel by many different decoding heads. So, we can have, all the same modules that we had in the AV stack before, but now they become more like multitask supervision heads and output heads rather than kind of the core cascaded chain that you might recognize from traditional AV stacks. And what's very important about this kind of an architecture is that it allows you to maybe investigate things like multi-frequency execution, right? Because maybe I have to execute motion planning at every single time step, but do I have to execute mapping or motion prediction at every single time step? Maybe not. Maybe I can do them every other frame. Maybe I can do them every 3 or 4 or 5 frames and save some computation and save some power actually for the onboard vehicle. And what we found was that when we actually implemented something like this and evaluated on all kind of standard benchmarks at the time, actually we were able to achieve, the same or slightly better performance on all these different tasks. But now with this opportunity to, turn on and off different heads, you're able to really vary the execution frequency of your approach overall. And we've since taken this core idea, this kind of archetype, and we've brought in what we've learned from foundation model training and development. So now rather than having like a standard transformer backbone, we switched to using an autoregressive llama backbone. And rather than just having AV tasks like object detection or motion planning, we've now actually brought in self-supervised, larger scale video generation tasks for training time. Of course, you would never run this kind of thing online, but what it allows you to do is it gives you this, powerful now options for other kinds of self-supervised losses that you can really shape your latent space in a very powerful manner. And what we did was, after developing this, when we had a preliminary model in hand, we actually applied it to driving, and we applied it. The videos I'm going to show you here are actually in a closed loop simulation and using that same photorealistic, all that technology I showed you before. And what we can see is that even with this kind of a preliminary stack, we're able to see, non-trivial driving behavior. So here I'm showing a right turn up above, and then below here I'm showing a left turn, unprotected left turn. And, these are, of course, preliminary results, but it's exciting to see that, such kinds of, such a stack and such lessons from foundation models can be brought in to that architecture and actually yield, a little bit more complex than trivial driving behaviors. Now, another caveat of this is, even though we were able to do this in closed loop simulation, and even though we're able to, have modeling the motions of agents and everything like that, one annoying caveat here is that we're still only able to reconstruct and simulate scenarios where we've already collected data before, especially for like the surrounding environment, like the static environment here. And what's we've also been looking at within the group very recently, this is a work that we just, I think, put up maybe in a matter of weeks ago, is an approach to allow us to actually generate scenarios in really any different kind of parts of the world, even parts that you don't have data. And what I'm visualizing here is exactly this architecture and how we do it. And in particular, what we do is we leverage the creative powers of video generation models behind the scenes. And so let's say, we want to have data from Tokyo and we want to actually drive in some kind of a Japanese city environment, but we don't have data that we've collected ourselves in order to actually use reconstruction. What we can do is, let's say take some kind of an initial context like a street view image or maybe a text description of some street or some area in Tokyo, and actually pass that through a video generation model. It could be any of your favorite video diffusion models, or it could be NVIDIA Cosmos, which is a very recently released framework for this kind of physical environment generation. And what the model will do is it will give us a video within that scenario. So it will actually it will actually generate different details of that scenario. It will drive through and generate kind of different aspects of perspective depending on how far away it thinks objects are. Now, of course, there can be visual artifacts with that generation. Right here, I'm showing how the grass kind of changes color as you drive through here, which, I mean, isn't really a real effect. This is, unfortunately, like a visual artifact that a lot of these models are prone to generate. And what we'll do is we'll take this generated video and then we will pass it through a neural reconstruction approach, which will give us a 4D reconstruction of the scenario. I say here 4D because if there are, mobile agents, will also be able to reconstruct those using, again, the kinds of techniques that we showed in the past. And I'm just showing here some example names of techniques that you can use with just video inputs. And we'll actually get a 4D reconstruction of this environment. Most importantly, as part of the reconstruction, we will enforce geometry. And so this kind of artifact where you have these transient temporal changes that are not real dynamics, now when you re-render or when you simulate within this environment, and here I'm showing an example on the right of, just following the exact same trajectory through that environment, but now in this 4D world, you can see that this artifact is now mitigated. Now the grass doesn't change color. And there's no more of this kind of transient temporal changes that aren't really actually existing in the environment. So this is something that we are particularly excited now, and we're developing actively to leverage NVIDIA's Cosmos, which is that recently released physical AI set of models, to really supercharge this approach and bring it sometime this year to everyone to be able to use as part of, for example, an NVIDIA inference microservice or something like this. Now, all of this is great and all, and I'm very happy to present this kind of work. But of course, a big question that remains in everyone's mind is how can we actually assure that these kinds of technologies are safe? Especially as we're now looking at bigger and better AI models to do a lot of these different tasks. So the way that we think about safety in the in NVIDIA and actually within the autonomous vehicle research group is that really there's multiple different axes along which you have to think of safety. And in particular, there's kind of three core areas that we've been looking at safety and bringing, working on different aspects of research to actually bring new capabilities in safety here. So the first is at design time. So when you're actually building your model, are you able to build a model and are you able to quantify its uncertainty? Are you able to bring in, for example, the specification of traffic rules so that your model maybe doesn't even, even at design time is not able to, for example, generate trajectories that maybe fall outside of the road, or maybe violate the speed limit beyond some percentage that you give. And then we have guardrails that you can bring in at runtime. So for example, we can do online monitoring of the output performance of models. And we can have, for example, a fallback stack or a safety system, which you can trigger if need be. We can also look at, for example, statistical guardrails, right? Like, can we use methods like conformal prediction or conformal regression in order to try and bring some guarantees of what we observed at training time to what we can expect at testing time. And then finally, there's also verification and validation. So once you have built a model, once you've trained it, once you have it ready in hand, what are the kinds of testing that you can do in simulation offline in order to stress test that model, in order to get a strong sense of, what kinds of performance can you expect online based on what you see offline, and what kinds of ODDs will it perform well in, right? What kinds of things can you simulate offline that give you confidence in the coverage, in the performance of this model? And even here, even for safety, there are ways that you can actually bring in foundation models to help a lot of this, in kind of some of these different axes of safety. And I'm going to show two examples here. So the really one of the first places that you can bring foundation models in is something that I mentioned earlier in the talk, which is for long tail robustness. When you have some of these kinds of more semantic anomalies, like if someone writes on a stop sign, or if you see a truck carrying traffic lights, which is otherwise a very, it's kind of benign, but an AV system might be quite confused. And something that actually I encourage everyone here to take a look at is the RSS 2024 best paper last year was actually given to a work by a joint work between our group at NVIDIA and the group of Marco Pavone at Stanford, where they actually showed that you can run at least the encoders of foundation models online in the car at runtime, and then you can check to see if what you're observing is an out of distribution, scenario based on these encoders. Obviously, I'm glossing over a lot of details, but I highly encourage you to take a look at that paper, which actually shows a example of exactly how you can use foundation models to bolster the long tail robustness of AV systems. And I think they actually have other robotic systems too that they demonstrated in that paper. So I highly recommend taking a look at that work. Another example is that we can use foundation models for offline safety evaluation. So one really difficult aspect of, if you do have a vast data set of driving, is figuring out what kinds of events happen in that drive, what kinds of ODD are you in, and you can do some of these with heuristics and maybe with human labeling, but very quickly that kind of stops to scale, or maybe the complexity kind of runs out of heuristic models. And so here we also believe that you can use foundation models to actually label and tag the kinds of scenarios that you have in your data set, and allow for much simpler data curation along certain ODDs, or along if you're trying to look for certain kinds of interactions between different drivers. We think that this is where foundation models, with their really powerful semantic understanding of the world, can help tag these different kinds of data, and ultimately search through a kind of offline data set that you might have to bring this kind of data to developers' hands much faster than we could before. So to wrap up here, I think foundation models bring a really new enabling capability that we haven't seen before in the past few years to AV development, to provide a really strong leap forward in the long tail generalization of AV systems. And importantly, they have the potential to empower the full AV program, not just onboard stacks, not just offline processes, even safety, really kind of all across what you would do to develop an AV stack. There's multiple ways that you can use foundation models. And, I think something that's also really important to say here is that when it comes to safety, foundation models are not magic. They're not fundamentally different than the kinds of black box models that we've seen last year, 2 years ago, 3 years ago, over the past decade, since deep learning has been really taking center stage. We do have strategies for deploying these kinds of AI-based systems. And the important thing to keep in mind is that we can bring a lot of these strategies forward and actually use them with foundation models too. And even at the same time, we can actually use foundation models and they can provide opportunities to actually improve the safety of autonomous vehicles. So with that, I want to thank you all very much for your time, and I'm very happy to take any questions.